So my attitude is, we're stuck here on this planet with these viruses like the one that I just described to you. Why don't we get them to start working for us for a change? Why do we always have to basically just always fight these? Can we put them to work and get them on our side for once? In other words, if we're handed lemons, let's try to make some lemonade. And I'll tell you about the harmless virus that my laboratory harnesses and puts to work on the next slide. So we actually use a type of virus called a bacteriophage. This is a virus that infects only bacteria. So it's totally harmless to humans. By the way, that's another characteristic of viruses. Viruses are exquisite in their host specificities. They will infect just specific hosts and nothing else. And that's an important characteristic that I'm going to come back to later. That ability to evolve specificity to bind to one particular host is an important characteristic of viruses, and it's something that I'll talk about very shortly. Okay, so on this planet, we're actually living with huge numbers of bacteriophage. It turns out there are approximately 10 to the 31 different viruses that infect bacteria on this planet. So that's a 1 followed by 31 zeros. And if you're like me, I bet you didn't even know there were that many particles on the planet. Okay, that's an enormous number. It's mind-boggling large. In fact, this is such an enormous number that we think that every bacteria found on the planet is being infected every 15 minutes by another virus. And because of this, these viruses keep bacteria in check. They actually slow down the propagation of bacteria. They have a major impact on the ecology that the bacteria have on this planet Earth. Okay, and if you know, this is how how this topic actually ties into interest in Earth system sciences. These things have a major impact on the ecology of the planet in this way. Okay, so here's just a few small examples of the zoology of these viruses, and they assume a fascinating range of different shapes and morphologies. For example, some of them have that lunar lander shape that I showed you on the previous slide, and then some of them, such as this filamentous bacteriophage, just look like skinny rods. And you know, if I go out actually to the water out here, say I go out to Crystal Cove and I pick up a liter of seawater, I'll find viruses that look like this in that liter of seawater. In fact, I'll find roughly 1 trillion different viruses that infect bacteria in 1 liter of seawater. Okay, so that's a 1 followed by 12 zeros. That's a really big number. There's huge numbers of the viruses on this planet, and we've characterized the tiniest of tiny fraction of those viruses. This is good news for us, okay? This is good news to me as a chemist. This means that there's an enormous pool of potential new molecular entities that I can tap into for my experiments, okay? The way I look at this is all of these viruses are an opportunity to do chemistry. All right, so here's what I want to do. My plan is to make these viruses work for us. If there's such enormous molecular diversity on this planet, let's start using it to do something useful. And specifically, I look at this big population of viruses as a net benefit. I look at this as actually this equivalent of lottery tickets, right? And you know, if you get more lottery tickets together, you're more likely to win the lottery. So if I can get together a big population of viruses, I know that I'm more likely to find, say, a new chemical reaction or a new protein that binds to some cancer-associated protein or something like that. Okay, so basically, I'm going to turn the tables on the virus, and I'm going to say, all right, you have this property of diversity, and instead of looking at this as very scary, meaning it's going to overcome the immune system and it's going to overcome pharmaceuticals that we throw at them, instead I'm going to say, all right, that big diversity is a strength, because it means that I'm going to be more likely to find useful molecules that I can use as a chemist. Okay, and I'll show you some examples of that in a moment, but each different molecule equals a potential lottery ticket. And we're going to only work with harmless viruses. And again, these things are exquisitely specific. So later when we take the tour of my laboratory, you don't have to worry about picking up, say, 1 trillion different viruses, because they're harmless viruses, and they'll just infect the bacteria that you're unavoidably associated with. Okay, so specifically, my laboratory is focused on 3 different research areas, and I won't have time to tell you about all of these today. In one area of the laboratory, we're interested in modeling how harmful viruses like HIV work. Okay, so viruses like HIV are constantly overcoming the immune system, or they're overcoming vaccines, or they're overcoming drugs that we throw at them. And our idea is to use the tremendous diversity of harmless viruses as a way to model that evolution of resistance. And so we actually have a system of anticipating drug resistance by essentially doing viral reconnaissance, using the harmless virus as a tool to model how drug resistance might emerge before it even has a chance to emerge. I won't have time to tell you about that today. The second area of my laboratory is very fundamental. I want to know what are the forces that hold together molecules inside the cell. So molecules inside the cell fit hand in glove fashion with each other. And it turns out there's a fascinating series of forces that hold together those hands and gloves. And we use viruses to pick apart that hand in glove type of fit and look at the very fundamental forces that hold together those hands. What actually makes the hand fit so well into the glove? So we actually look at that using viruses as a way of doing high throughput dissection of such forces. And again, I won't have time to tell you about that topic today. Instead, what I thought I would do is focus on a new area of my laboratory. This is a collaboration with Professor Reg Penner in my department, where we're focused on using viruses in electronics. So what I want to do here is I want to use the ability of viruses to evolve specificities and then put those specificities into electronics so that we can confer upon the electronics that type of specificity. Okay, I'll show you exactly what that means in a moment. Right now that sounds really abstract, but I'm going to get into the specifics in a moment.